Hello. Today we present the term project proposal of Team 9, analyzing the effects of energy benchmarking on building energy consumption for cities in North America. The building sector is currently responsible for approximately 14% of greenhouse gas emissions in Quebec. Furthermore, a US study estimated that total electricity consumption could increase by up to 35% by 2050. To reduce the future load on the grid, we propose studying the energy consumption of existing buildings.
One way to tackle building energy consumption is through energy disclosure ordinances. An energy disclosure ordinance is a law that requires building of a certain size and type to track and report, also known as a benchmark, annual energy use. This information is public in the hopes that benchmarking leads to improvements from building owners. This map shows the mandatory benchmarking policies in the US, while Canada has only one mandatory program in Ontario. The goal of our project is to determine the potential benefit of implementing such a program here in Montreal. Our first objective is to identify the attributes with the largest effect on energy use intensity, also known as EUI and greenhouse gas intensity. We will then look at each city individually to determine if there are changes to the EUI and GHG intensity 4 years after benchmarking began. Our third objective predicts change in EUI and GHG intensity for a set of buildings in Montreal.
To determine the key attributes for Objective 1, Pearson correlation will be used to evaluate the strength of correlation between numerical attributes such as gross floor area and our target variables of EUI and GHG intensity. Spearman correlation will then be used for attributes comprised of categorical data such as the ASHRAE climate zone. Performing the correlation analysis will allow us to remove attributes showing little or no correlation, as well as identify the attributes showing the strongest correlations to the target variables, which will then be used for the preceding objectives. In Objective 2, we determine whether the Energy Disclosure Ordinance affects the EUI and GHG intensity. We will first classify buildings based on their EUI and GHG intensity from very low to very high. This will be done for both the Year 1 data, which represents the first year that the ordinance went into place, and the Year 4 data, such that we can make a comparison in Step 2. Histograms will be used to see the number of buildings classified as low or high EUI, as well as analyze the different averages and standard deviations to note changes from Year 1 to Year 4. Finally, we can also make comparisons between the different cities to note any differences in key attributes or effectiveness.
Our next objective aims to predict whether an energy disclosure ordinance would affect EUI and GHG intensity of buildings here in Montreal. We'll first train individual models for both Year 1 and Year 4 using data from all cities, excluding Montreal, to classify buildings into 5 levels of EUI and GHG intensity. We'll evaluate the performance of the KNN and decision tree algorithms, and the final model will be used to classify the EUI and GHG intensity for a set of buildings in Montreal. An analysis of the prediction made by the model would determine the expected effect of disclosure ordinance for the city. To address Objectives 1 and 2, we obtained building energy use data from 7 cities in the US and Ontario for at least 4 years per location, with Year 1 being the first year of energy benchmarking. For Objective 3, a sample set of buildings in Montreal was obtained.
From the open data portals, we obtained 6 attributes regarding the building itself, as well as 2 target energy and emissions variables for approximately 1 to 5,000 buildings per city. To better contextualize the building energy use, we use the zip or postal code for each building to extract 4 socioeconomic attributes from public government data, while 12 regional climatic attributes were obtained from ASHRAE standards. Some early findings from Boston are included as an example. We looked at the breakdown of building uses in the pie chart, which corresponds with the color of the bubble in the second chart. The second graph shows EUI on the x-axis with respect to building age on the y-axis, and gross floor area as the size of the bubble. We can see from the seafoam green bubbles that many large healthcare buildings are associated with high EUIs compared to office or residential buildings, and the highest EUI came from one manufacturing building for this dataset. We still have to cross-reference and merge data sets, address missing data, and remove outliers for a few of the cities. We will then analyze the cities on an individual basis, followed by completing the analysis as outlined in Objectives 1 to 3. Thank you for taking the time to review our proposal, and we look forward to receiving your feedback.